Yes, I think we are ready to start now.
Great.
Yeah, so this is the title of my presentation. And today we are going to be talking about partition arrays, which is yet another software tool that I implemented that I know that some people are using it to do larger scale simulation. So this partition arrays is essentially like the linear algebra backend that we are using to distribute our finite element codes. So yeah, I think it has been also a pretty successful software package. And here I'm going to talk about the key ideas behind it. So as you said, this software is implemented in Julia, but today's presentation is not Julia specific. So I'm going to try to explain the key design ideas behind this library. And I think these ideas extend to other programming languages as well. So I think the presentation can be useful even for people that are not really interested in Julia. So here we are going to be talking actually about a new programming model to do distributed computing, which I think, yeah, goes beyond Julia itself. So this is what I have prepared for today. So we're going to talk a bit what PartitionedArrays is. So what is this library for? Which type of tools we have in this library? And yeah, but most importantly, as I have said, so we are going to discuss this new programming model that we created for PartitionedArrays in order to implement all these distributed algorithms. So we are going to present what about this model, how it works, and also how general and efficient and convenient it is, right? And finally, in the next part of the presentation, since I have some time, so if I'm not wrong, this is like 45 minutes presentation, right?
Yeah.
So at the second time, we will have time for some live demo. By the way, I will be happy to answer questions during the presentation, okay, and especially during the live demo, okay. So during the presentation, questions are optional, but during the live demo, I would say that some questions should be mandatory, right? So if you have questions during the live demo, don't hesitate to unmute your mic and just ask your questions. Okay, so I think we can start with this. So first of all, let's talk about what PartitionedArrays is, and let's start with a very simple example, right? So imagine that you have this system of linear algebraic equations in which the matrix is a sparse matrix, and now your problem is to solve for vector x. So this is a very simple problem, right? When the sparse matrix is small, you just need to take your laptop, take your favorite programming language. In this case, we use Julia, which has also support for a sparse array. For sparse arrays, you build your sparse matrix, you build your vector, and you use backslash, and bang, you have the solution. So for this type of problems, solving them is pretty straightforward. But now, of course, in the real world, in the real world applications, we want to solve this type of systems that result from the discretizations of PDEs. And in this case, the matrix has like a lot of rows, so it can have millions or even billions of rows, and solving the system is much more challenging, right? So you cannot use backslash in your laptop anymore. So you want to use a supercomputer and a solver library that implements parallel solver methods to solve this problem in parallel in a supercomputer. And essentially, this is what we are doing with PartitionedArrays. So it provides tools to solve sparse linear systems on large-scale distributed memory computers. Now, at its core, PartitionedArrays provides two basic data types. So a distributed vector called P vector, and a distributed sparse matrix called P sparse matrix. You have some representation of these objects here that allows you to distribute your computations among different MPI ranks. And at this point, you can think, okay, so this kind of functionality is not truly new in PartitionedArrays. Is already available in other libraries, right? So there are very well-known libraries like Petsy and Trilinos that provide similar functionality. And I think the first question I want to answer is why we decided to create a new library, right? So what is the added value of PartitionedArrays with respect to these other libraries, which, by the way, are very well-known projects, very well-funded projects, with a lot of tradition and expertise behind them. So why we want to create another sparse linear algebra library? I think there are two reasons or two novelties of PartitionedArrays. And the first one is that it's fully implemented in Julia, which is a relatively new programming language. Whereas the other libraries are implemented either in C or Fortran typically. So there is some novelty here. So if you're a Julia fanboy, maybe this is a fangirl, this is maybe enough for you, right? But for me, this is not the most interesting part of partition arrays. What I think is the key novelty here is a new programming model that allows you to implement distributed algorithms. And in particular, this programming model allows you to do a pretty fancy trick, which is decouple the logic from a distributed algorithm from the number of processing units running the distributed algorithm. So this may sound a bit abstract. So I have a concrete example to illustrate this idea. So here, so in this slide, this is the screenshot of a Jupyter notebook, and I have not added extra workers or extra MPA ranks in this Jupyter notebook. So this is running in a single sequential process. And here I'm solving this very simple example. So this is really a hello world example, right? So I'm building this vector of length 9 distributed over 3 parts, and I'm computing the norm of this vector using partition arrays. And as you can see here, so the syntax to solve the problem is not really that important. What is important is that even if you are running in a single process, so in this Jupyter notebook, you're able to inspect the partition, the data partition of this vector. So you're able to inspect all the logic needed to distribute the code. And this is true for the data distribution, but it's also true for all the logic needed for doing communications, for instance, right? So you can also check if the send IDs are matching the receive IDs, and you can check the send buffers, the receive buffers, etc. Yeah, in a single process, which I think it's pretty useful, especially for debugging. But of course, at the end of the day, once we know that we have a valid code and we have done the debugging in this sequential mode, we want to run also large computations on supercomputers, right? So the same code with really small modifications can also be deployed in a computer cluster. Okay, so this is essentially the same example, but now you need to copy all the code in a file. We are not working with Jupyter notebooks on clusters yet, so this is one of the future projects actually. For the moment, you need to copy everything into a file, and then put all your code inside a main function, and use this function provided by PartitionedArrays called with MPI, which essentially deploys this function on a supercomputer. So here you can switch from a sequential execution to a parallel execution in a supercomputer. And this is what allows you to have like the best of both worlds, right? So you can use a Jupyter notebook for debugging and prototyping, and you can have then also a real parallel code, a real distributed code running on a supercomputer. Okay. I see one notification in the chat, so maybe Bernat, you can tell me if there is some question in the chat.
Yeah, I think that someone joined with some AI note taker stuff. Actually, I'm gonna delete that because it's not a question actually.
Yeah, I'm not looking into the chat. So if there is some question,
I will.
Please let me
Sure.
know. Yeah, so this is the key idea, right, of the novelty of the library. So you can inspect the logic of your distributed algorithm in a single process, but you can also deploy the algorithm on a supercomputer. Now the question is how this works, right? And I think the ideas behind are quite simple. Okay, they are not that difficult. I think the merit of the library on all this model is to really so implement these ideas and make them real and make them efficient for real world computations. Okay, so I'm going to try to explain the key ideas behind the library with these small examples. So continue with this small example of the vector partition in 3 parts. And the first idea is that we need a model for representing data partitions. Okay, and here what we do is, okay, so I have a vector distributed in three parts, and I can represent this in a sequential process. So I can represent this in your laptop using an array container. So I can represent this using a vector of vectors. Here I have a vector of length 3, and at each position of the vector, I have a sub-vector, which represents the subpart in which I have distributed my original vector. And this can be, this can be stored in a sequential process in your laptop using a standard array type. So, for instance, the standard array type in Julia. So this is going to be a vector of integers. But of course, you want also to run this with MPI, and then when you go to MPI, we are still using with a vector of vectors, right, conceptually, but now this vector has a different type. So the outer vector, it's an MPI vector. An MPI vector means that the items of the outer vector are distributed over MPI ranks. And in this case, so we have 3 items in the outer vector. So here we will need 3 MPI ranks to run this computation in parallel. Okay. So here the only difference between the sequential execution and the MPI execution is the particular vector type that we are using under the hood. Okay. So here we have like an interface that works for both vectors types, and then we have 2 particular implementations, one for the sequential case and one for the MPI case. Okay, and for the MPI case, we assign each one of the entries of this vector to 1 MPI rank, and this is why this is running on parallel eventually. So in summary, what we are able to achieve is to decouple the number of parts in which we partition the data in a distributed algorithm from the number of processes that is running this algorithm. And we have 2 cases of interest. So when the number of parts is greater than 1, but the number of processes is equal to 1, so this is for debugging. And then the other case in which is the case in which both the number of parts and the number of processes coincide, which is when we deploy this with MPI in a computer cluster. Okay, so at this point, so the benefit of having these 2 modes maybe is not that clear, especially if you have not used MPI a lot. But if you are a seasoned MPI like programmer, you can start appreciating why this is useful, right? Especially having the possibility of debugging in a single process is very, very useful in practice, right? Because MPI debugging is a very hard problem, actually. Okay, so imagine that you have a parallel computation running on several ranks, and you have a bug in your program, and this bug manifests only in a subset of the ranks. Here, a lot of very bad things can happen, right? For instance, you can have deadlocks. So if this rank is waiting a message for this other one, but the message never comes because the other rank crashed, so you will have a deadlock. And debugging this kind of errors is really, really difficult, really, really challenging. Now, when it comes to debugging tools, so let's start with the simplest one, so print statement debugging. So if you try to use print statement debugging with MPI, it's not that good actually, because the screen output is very cluttered and non-deterministic, because you have several ranks trying to write to the same standard output, and this can cause any race conditions. So this kind of output. So this is like the hello world example in MPI. And even this very simple example in which each rank says, hello, I'm rank 1 from 8, right? So even in this very simple example, if you run it with a large enough number of ranks, you get a very ugly output. And this is only with 8 ranks. So imagine if you need to debug your code with, say, 100 ranks. So it's going to be very, very challenging. Now, if you want to be a bit more sophisticated and use a debugger, you can try to use any sequential debugger also to debug MPI code. And here in theory, you can do this by running MPI exec and deploying several instances of this sequential debugger running each one of the ranks of your MPI computation. But now it's going to be very challenging, right? Because you will need to advance all these instances of the debugger one by one. You will need to set breaking points, etc. So I think it's pretty unpractical to try to use sequential debuggers when working with MPI. Yeah, and if you're even more advanced, you maybe have used MPI debuggers. So there are not many of them. So there are a couple of well-known ones, which are often like proprietary software. So they are available behind a paywall. And still, even with the most advanced MPI debuggers, debugging MPI code is still very, very hard because you are not solving the fundamental issue here, so, which is that you are having several processes running in parallel, and you will have a lot of type of problems associated with this parallel execution. And this is what we are trying to solve with partition arrays. We try to reduce as much as possible the need of doing parallel debugging. And I think we have managed pretty well so far. So I think in 99.99% of the cases, if the code works with the sequential backend, it also works with the MPI backend out of the box. And if not, it's because we had a bug in the MPI backend. Yeah, but my experience is it's pretty robust. So if the logic of your algorithm works well with the sequential one, it's going to work well also with the MPI one. Okay, so this slide is to discuss a bit how this relates with other programming models, right? Because you can do parallel computing in many different ways and flavors. And here we have this table with two axes. So we have here this axis telling if you are using essentially one memory space or several memory spaces, meaning if your data is like shared in one process or split in multiple processes. And in the other axis, we have if the data partition is explicitly hard-coded in your algorithm or not. Okay, so for instance, in MPI, you need to explicitly hard-code the data partition. So you need to implement your algorithm from the point of view of each one of the MPI ranks. Whereas when you're using multi-threading, you don't need to do this, right? So you work with global indices and loops of global length and you don't need to work with local. Yeah, you don't need to organize your algorithm using like local indices, for instance. Now the combination of these two axes give four possible alternatives here. And in the diagonal, we have like the two well-known models. We have MPI and OpenMP, or multi-threading in general. So in MPI, you have several memory spaces, several processes, and the data distribution is hard-coded in the algorithm. Whereas with OpenMP, you have one process, but multiple threads in this process, right? All of them consuming the same memory space, and you don't need to partition your algorithms. But of course, there are also these two other options here on the outside the diagonal. And here we have the PGAS models. I don't know if you have heard about them before, but I mean they are not that popular as popular as MPI, but they have some track record also in scientific computing, especially for instance in libraries like Fortran. So you have Fortran coarrays. So Fortran coarrays is a particular implementation of PGAS. And here the idea is to try to use distributed memory machines with an MPI similar to multi-threading. So with PGAS, you are working with several processes, so in a partitioned memory space, but the API is logically shared. So it's very similar to multi-threading. And then you have this PGAS library that handles all the communications under the hood for you. You don't really need to specify the communications explicitly, which is much better than MPI in this sense, right? So you get communications like for free, but performance can be a bit challenging. So predict the performance of these algorithms can be a bit more challenging. And then we have this other quadrant here. I don't know of any programming model that falls here actually. But I know that people are using this idea in practice. So for instance, I remember the first time I implemented a domain decomposition algorithm. It was in MATLAB in a sequential process, right? And I packed all the subdomains in a vector and I processed all the subdomains one after the other, just to double check that mathematically the algorithm makes sense, right? So I was trying to implement an algorithm in this situation here. So a logically distributed algorithm in a single process, okay? And with partition arrays, you are doing this actually. But the nice thing of partition arrays is that the same code can work here, but can also work here with MPI. So we cover all these rows. So for debugging, you can use the physically shared memory space, but for deploying in a computer, you can use MPI. So we have the two options when using partition arrays, which I think it's pretty useful. Now, so let's continue discussing about how this works in practice as well. So now we have a model for the data partition. We're using these arrays containers, but now we also need a model for the computation, right? Because you want to do something with this data. And in particular, we need to model computation and also communication, because these are the two key things you want to do in a distributed algorithm. And for this, we have an interface. So we have a set of functions that all of them are defined as operation on arrays. So all of them make sense for any array type. And in particular, they make sense for a standard array. So that's why these functions work on a laptop. But they also make sense for this MPI distributed array. I have some examples here. So the function map. So this one manipulates items in the array element by element. So you define a function f, and you want to map function f element by element to all the items in the array u. And yeah, when you are running in a laptop, this can be implemented with a for loop. So this is pretty straightforward. And when you are running with MPI, this is as simple as applying function f in parallel to the local data stored in one of the MPI ranks. Okay, so this map function represents parallel computation in our model. Here you have an example, right? So this array, if you map it with this function, you will get this result. And when running with MPI, so the input array is going to be distributed in this way over the MPI ranks, and the result is going to be distributed in this other way over the MPI ranks. Now, we have also some functions to model communication. I don't have time to go over all of them, so I'm going to illustrate only two of them, one for collectives and one for point-to-point communications. So let's start with the collective communication. So a gather. So how we model a gather with partition arrays. So gather is a function that takes an array v and returns an array u, and it's defined in this way. So the output array is defined like this. So in component J, you're going to have all the input array, and in the other components, you're going to have an empty array. Again, this can be implemented for a sequential array, but when you're with MPI, if you want to implement this operation, you will need to do communications, right? So because in order to build this data in this rank, you need data in other MPI ranks, and you will need to do communications to implement this function. And you can very quickly see that these communications coincides with an MPI gather. So that's why we call it gather. So this is like the array version, the array model of an MPI gather. Yeah, we also have scatters, broadcasts, scans, reductions, all gathers, etc., following all this same idea. Yeah, and finally, we also have a way of modeling point-to-point communications, and this is typically useful when you are doing stencil operations or when you're doing domain decomposition methods in which you want to communicate with a small set of neighboring processes. And we model this using directed graphs. Okay, so you represent with an array the graph describing the communication. In other words, the number of the processes in which you want to send data. In this case, so the first entry of the array has indices 3 and 4, meaning that the first process wants to send data to process 3 and to process 4, right? So the second process wants to send data to 1 and 3, etc., etc. And with this, you build this graph, which represents this communication pattern. And then you define also the data to be sent, to be communicated. In this case, you say, okay, in the first process, I want to send number 30 to my first neighbor. And the first neighbor, if you remember from the previous slide, was process 3. And I want to send data 40 to my second neighbor, which is process 4. And the same for the other one. So essentially, the send data corresponds to some values on the edges of this graph. And finally, once you have like the graph and the data you want to communicate, you have this function exchange that does the communication. And you get another array containing the data, but from the receiving point of view. Okay, in this case, The first entry is the data received in 1. So in 1, I received 10 and 10 because 2 sent number 10 to 1. And what else? Yeah, and 3 also sent number 10 to 1. So you see, you have the data, but sorted now from the incoming direction. Yeah, and with this, we model this point-to-point communications. And under the hood, we are using I sends and I receives to implement this function when using MPI.
So Francesc, one question about this.
Yes.
Okay, maybe I think it's on your next slide actually about how efficient it is, because you are doing some wrappers of MPI functions already. So yes. Do these interface or these wrappers that you implement have any kind of overhead compared to pure MPI?
Yeah, so I think this is a very good question. Yeah. And also very pertinent one and very predictable one, I would say. Yeah. So I have some to discuss about this. And I think there is this question, but there are also 2 more questions related with this one. First, because as you said, we are building a layer on top of MPI, and this may have some potential issues, right? That I want to discuss now. First of all is, okay, how general is this? Right? Because MPI, so it's really, really big. So you have 1,000 pages in the MPI standard, and we don't have 1,000 pages in our documentation. So it's more restricted, right? So how efficient? So which kind of algorithms you can implement with partition arrays and which kind of algorithms you cannot implement with partition arrays? So the MPI is going to be much more general for sure. Also efficiency. So does this interface introduce overheads and how big? And finally, how convenient is in practice. So if it pays off, right, to introduce this layer or not. So we are claiming that prototyping now is much easier, but is this true in practice, right? So I think this is also another pertinent question. So I have some slides to discuss about this. So about if this is general enough. So I think I have a practical example. So on top of this interface, we were able to implement all things needed to have a distributed finite element code, okay, running on a supercomputer. So in this sense, I think it was general enough, at least for our applications. And if you look into the model, this model is going to work for any data parallel algorithm. So if you have an algorithm in which the way of solving the problem is to split the problem into pieces, right, and distribute these pieces, partition arrays is going to work pretty well. So in the situations that is not going to work that well is when you want to do more task-based parallel computing. For instance, if you want to implement a thread pool, partition array is not going to work. So you will need other type of parallel computing libraries to do this, okay? But for data parallel algorithms, so the domain decomposition, finite elements, so working with distributed matrices, vectors, etc., partition arrays is general enough, and this is proved by our experience. So we had all the ingredients needed to implement a distributed finite element code, and the same applies for a finite difference code, finite volumes, etc., etc. Yeah, now regarding performance, they have some slides to talk about the performance, and here I'm showing some kernels implemented in the library. So this is the performance of the sparse matrix vector product. Here we are multiplying a very large matrix times a large vector in parallel. So this is a strong scaling example in which you see the time, the wall time versus the number of CPU cores for different problem sizes. And here I'm comparing against PETSI, which is like the gold standard, in this field, which also implements similar algorithms. And as you can see, and by the way, the matrix is a 7-point stencil, so a 3D Laplace operator. And for this case, so partition arrays is as fast as PETSI, and in fact, even a bit faster, as you can see. So I think this proves that you can implement algorithms efficiently, so using partition arrays. Yeah. And in particular, the sparse matrix vector product, which is a very important kernel if you want to do iterative solvers, for instance. Yeah. And I think that PETSI in this case is a very strong baseline because this kernel is so important that I guess that people in PETSI have spent a lot of time to try to optimize the sparse metric vector product, right? Because it's one of the bottlenecks typically in scientific computing. So yeah, so we can assume that PETSI is a very highly optimized version of this algorithm, and we are able to be as fast as PETSI or even faster in this example. So you have more kernels, and also these other slides also discuss how effective is this programming model to implement new algorithms. So this is the sparse matrix product. So now it's matrix times a matrix. The same with the strong scaling tests, and we compare partition arrays and PETSI. And this was implemented by a master student. So with this, I would like to show you that even a student that has not like years of experience working with parallel algorithms can implement efficient algorithms using partition arrays in a relatively small time frames, for instance, in a master thesis. And here they have like the comparison against PETSI. Now the red lines are partition arrays and the blue lines are PETSI. And for the first version of the product, in which we do both the symbolic and the numeric phase, partition arrays is consistently faster. Yeah, and this is a really large computation. This is 16,000 CPU cores in the largest case. And when you consider only the numeric phase, PETSI seems to be slightly faster in some cases. But in any case, my point is not to be faster than PETSI, it's just to illustrate that with partition arrays, you can be as fast as PETSI. Yeah, and we also implemented a related algorithm, which is like matrix transpose matrix product, which you need slightly different communication patterns, and you can also implement them with partition arrays. And here, both when you have the symbolic and numeric phase, and when you have the numeric phase, partition arrays was consistently faster and significantly faster than PETSI. Yeah, I think I was very happy to see these results by my student. Yeah, so you see the gap between the two libraries is pretty significant in this kernel. Yeah, I have another one, also a master thesis from another student, and this is an implementation of the high performance conjugate gradient benchmark. So this is one of the well-known benchmarks in scientific computing, which essentially is a conjugate gradient preconditioned with a geometric multigrid to solve a 3D Laplace operator. And there is a C++ reference implementation on the internet. And this project was about, so implementing the benchmark using partition arrays and comparing against the C++ baseline and get some results. And here you have a weak scaling. So this is a weak scaling experiment up to 32,000 CPU cores. Yeah, so this is not the kind of results, the typical way of representing the results of a weak scaling test, but this is what is done in the benchmark. So you want to see that the more CPUs you add to your cluster, so the flops, the number of operations you can do in a second increase linearly, right? So this is like the expected result, a linear increase of flops versus CPU cores in this weak scaling test. And here you see in orange the Julia, so the partition arrays, and in blue the C++ performance. And in some cases we are a bit faster, so more flops, and in some cases we are a bit slower, but you see that we are able to be as performant as the C implementation. Yeah, I think this was the first parts from the slide. So I think the key messages here is that in partition arrays you have a distributed sparse linear algebra library like PETSI or Trilinos, but the novelty is that it has this new programming model that allows you to decouple the logic of your parallel code from the number of ranks that you're using to run the algorithm, which is pretty useful for debugging, but this is still efficient as you saw in these experiments. So it's free and open source, and it's available in this, on GitHub in this repository. Yeah. So this was my first part. So I was planning to do a demo, but since we have only 5 minutes left, maybe we can start now with a run of questions regarding this part, and maybe I'm going to send you the notebook of the demo separately so that you can look into this later. So I think it will be nice to discuss a bit now about this part. Yeah.
Sure. Yeah, thank you. It's super interesting. And I have a few questions. People can also ask questions. They can mute themselves or write it in the chat and I will read it. Anything can work. So maybe just to get started, you talk about having two different backends. One was array and one was MPI array.
Yes.
Of course, a lot of people here, I know, for example, for sure, Filippo, who is in the room as well, is interested in seeing how this would work when you use GPUs as your multiple devices, as your processes.
Yeah.
Have you tested this with an MPI, for example, Q-array backend, or do you have plans to do that?
Yes, we are working on this right now, actually. Yeah, and you can use MPI arrays to communicate several GPUs. Okay, so this is the partition arrays does the data distribution, and now when you process the local part, you can use GPUs for this. So you can use like MPI plus CUDA, so it's going to be like partition arrays plus CUDA, and locally you want to be running CUDA in each one of the processes.
Right, but you communicate from and to GPUs without going through the host, no? You don't have to go
Yeah,
through
so we want
host.
to implement this efficiently, right? So that you communicate from GPU memory to the GPU memory, yes.
Okay,
Yes.
okay.
But
That would be very
since
nice.
our backend is already using MPI, and if you configure MPI with CUDA-aware support, so with CUDA, so CUDA-aware MPI, I think this should happen quite automatically, as long as the buffers are already on the GPU.
Right. Yeah, I see a thumbs up for Filippo from Filippo, so I think that's good enough.
Yeah.
Okay. Other questions before the live demo? If anyone has any question. Okay. Maybe I can do another one, which you mentioned about that you were doing this in Julia, not because you are particularly like a fanboy of Julia, which some people here think that I am, but I'm not that much. But what is the strongest reason why you chose Julia? I mean, you could have done this in other languages as well, right? So why did you choose Julia?
Well, because I mean, I have a finite amount of time to implement these things, and Julia tends to be pretty good to implement a lot of code in a short amount of time. Yeah, so I think this is the main reason. Yeah.
Okay.
And you get and you also get efficient code at the end of the day. Yeah, I think this is why I consider Julia. Yeah, it's like a practical choice. Yeah, and also it's a language that is big. Yeah, it's starting to get interest in the scientific computing community, right? So yeah, I think can also be like another selling point of the library. Yeah, for some people.
No, I agree. I mean, you can show these examples that you can just run with a few lines of code, and like also installing and running, it's almost nothing compared to other languages. So I always agree with that for sure. All right. Any other questions? If not, then maybe we can move to the live demo, Francesc.
Okay, so I thought we were already out of time, but so it's
I mean,
a surprise. We have 10 minutes, maybe?
We typically schedule 1 hour, right? So if we finish around 6 p.m. and it's not a hard, let's say, constraint, we will be fine. So yeah, there's some time.
Okay, so yeah, then I'm very happy to be able to do the demo, of course. Yeah. Yeah. So for this, I have prepared this Jupyter notebook. Okay. I have some problem with my Zoom. No, I'm not able to select this. No.
Yeah, sharing the screen with Zoom is very annoying because it blocks part of your screen and then
Yeah,
you
it's blocking part of my screen, so especially the part I want to use now. Okay, so let me stop sharing and I want to reshare again, okay?
Sure.
Okay, I'm ready now. So let's try to do this demo. And here we are going to learn about the basic usage of the library, right? So if you want to solve a linear system with the library, you will need to build a matrix first, to build a matrix in parallel, and then to solve a system with this matrix. And I'm going to try to give you the gist of it. So let's consider a very simple example. So this small matrix, and we're going to distribute this matrix into two parts, just in this example. And let's discuss how we can do this using the partition arrays. Yeah, so this is a Jupyter notebook running Julia. So this is another reason to use Julia, because it's very useful also for teaching purposes, for instance, because you can use Jupyter notebooks quite easily and still have like efficient code. Okay, so let's start by loading the data dependencies. And after this, the first thing you need to do when working with partition arrays is to creating a vector containing the part IDs or the rank IDs. In this case, I want to split this into two parts. So a vector containing the IDs of this part, so 1 and 2. Then I need to define the partition of the rows in my matrix. And for this, I can use this function uniform partition, which takes the rank IDs and also the number of parts I want to use and the total number of rows, which in this case was 6. And this provides you with this vector of vectors describing you the row partition. So when you see this vector of 2 entries, you need to visualize that when running with MPI, you will have 2 MPI ranks, and the first MPI rank is going to store this part, and the second MPI rank is going to store this other part. Now we have the row partition, so we can like create the values of the matrix. And here, so there are several options, but the simplest one is to create the coordinate vectors of the non-zero values of your matrix that appear in each one of the parts. So in part 1, I want to create the coordinate vectors for all these non-zeros, and in part 2, I want to create the coordinate vectors for these other non-zeros. And this is done by this function. So in this create CO takes my local row ID. So this input here is going to be this vector in rank 1, and it's going to be this vector in rank 2, right? And using map, I can apply this function element by element or rank by rank to this other vector. And this is the way we can construct the coordinate vector, right? So you see, so for instance, here I have in row 4, column 4, I have value 2. So row 4, column 4, value 2, and row 4, column 3, I have value -1. So row 4, column 3, I have value -1. Yeah, and the same for the other one. So this is how these non-zero values are now split in the two ranks. And when you work with partition arrays, so you end up using a lot the map function, because this is the way we represent like the parallel parts of the code. And when using map, you need to define auxiliary functions all the time. But fortunately, in Julia, you have the do block syntax, which you can define these auxiliary functions in a very convenient way. So you don't need to provide a function name. You just create a do block here, and it's the same result. So these kind of things, if you work with partition arrays, you're going to be doing this quite a lot. Yeah. So now that we have the coordinate vectors, we just need to assemble the matrix. Yeah, so I don't have time to discuss the details, but this piece of code takes these coordinate vectors and creates the final sparse matrix. So we have a 6 by 6 matrix in this case, partitioned into two parts. Okay. Now, so the first thing you need to realize when working with this object, this matrix object, is that you cannot index it directly. Okay, so if you try to index at position 3, so row 3, column 4, it's not going to work. And this is not implemented for performance reasons. Because when working with MPI, this value can be stored in a particular rank, and you are asking for it in all MPI ranks, right? So you will need to do a lot of communications, and this is not efficient. So you need to write algorithms without indexing directly the matrix. You need to do this by using the underlying data partition of the matrix. I'm going to show this later. But for debugging, you can always convert the parallel matrix into a sequential one with this function, centralize. And this one gathers all the pieces into a sequential matrix, which, by the way, is very useful also to double check that things were implemented correctly. So you see that this matrix is this matrix here. Now, if you want to work with the data, right? So you need to go to the data distribution of the matrix. And here we use split format. So this is the idea behind this is pretty much what you have in Betsy as well, right? So you're going to store the rows in the first process in two blocks, one containing this diagonal block and another block containing only the non-zero column. So in this case, it's going to be only this column. And you can you have access to this data with this function. So on values gives you the diagonal blocks. And in this case, you can visualize them like this. Yeah, so this is the own block in part one and the own block in part two. And you can also use the own ghost to see the other block. And here in this case, there are just like one column in each one of the parts. Okay. Yeah, and if you want to run this with MPI, you need to put everything into a code. I don't have time to discuss this in detail, but you put everything inside a code, inside a main function, and then you deploy this main function with MPI function. And then you can execute your code like this using MPI exec as any other MPI application. Okay. Now, so this is how you create the matrix. And now we have a matrix. We want to solve a system, right? So I'm going to show how you can use some parallel solvers here. And I'm not going to use this very simple matrix because it was too simple. I'm going to use a bit larger matrix obtained by discretizing the Laplace equation on a 3D grid. And here we're going to consider n plus 2 points per direction and p parts per direction. So in this example, we will have four parts, so 4 MPI processes. If you run this with MPI. So I have a function that builds the 3D Laplace operator. So this Laplacian fem in which you need to provide the number of points per direction and the number of parts per direction. So in this case, 27,000 rows and columns. And again, you can now look to the own values, but they are going to be slightly larger matrices, right? So they're going to be 8 blocks. Yeah, and each one of them is around 3,000 entries. Yeah, so you can inspect even for this large matrix all these blocks. And then we have also the own ghost values. Yeah, which are these rectangular matrices containing the non-zero columns in each one of the parts. Okay, so we have the matrix. Now we need a vector to be able to solve a linear system. Here, just for example, as an example, I'm building a vector full of ones with this function. And the same as for the matrix, you cannot index this vector directly. So for performance reasons, you need to access the data partition directly if you want to use it. Okay, and the vector is only on values. This gives you the values stored in each one of the parts. Okay, so now let's solve the system. And for this, we use this partition solver. So this is also inside the PartitionedArrays repository, but it's implemented in a separate module. All the linear algebra is in PartitionedArrays. So all the arrays and vectors are in PartitionedArrays, and the solvers are in partition solvers. Now, to solve this problem, we need to create a linear problem object, which also contains an initial guess of the solution. Here I'm using a vector full of zeros. And now for the solver, I'm going to use a conjugate gradient with some tolerance. Okay. Yeah, now I have like the solver object. So I solve it. And here we are going to see all the iterations to solve this large matrix. So since this is a pretty large matrix, I would expect a large number of iterations because we are not using a preconditional, right? So you can get the final solution with this function. And finally, you can check that it was computed up to the tolerance required. So we require 10 power. So we require, let me check here. Yeah. So -9, 10 power -9, and the residual norm is inside these tolerances as expected. So maybe in a couple of minutes, I can explain how to use a multi-grid preconditional, right? So let's like reset the solution to use again an initial guess of 0. And now you can build a preconditional with this syntax. This is going to be an AMG1. And now you can build the solver object using the preconditional here. Yeah, now this takes a time, not because the matrix is large, because now Julia is compiling quite a lot of code. So because the AMG part is, some lines of code involved. Yeah, so once it's done, it's pretty fast. It's not, when it's compiled, it's pretty fast. And now let's solve it with the multi-grid preconditioner. Yeah, and you see, we were able to cut down the number of iterations significantly, right? While still converging to the same tolerance. Yeah, maybe I can stop here, maybe just to finalize. So you can tweak a lot your multi-grid preconditional, right? So multi-grid methods are infamous to have a lot of parameters, and you can also specify all the parameters. So which prism method you want to use, which type of cycle, which coarsening strategy. Here we use a smooth aggregation. Yeah, which core solver, how many fine levels, which the core solver size, etc. So all these kind of things you can also do in partition arrays. Okay.
So that's a good point, Francesc, because sometimes if you want to access different parts of the algorithm, for example, of an AMG solver, right? You want to change however the prolongation or the reduction operations are done. I think PETC gives you some kind of API to access those. Like you can modify the algorithm at will. And would you think that you have the same level of flexibility with partition arrays?
Well, this argument here is expecting a function with a certain signature, right?
Yeah.
Yeah. So essentially a function that returns a prolongator. Okay. And so if you implement your function, then you can plug it here and it's going to work. Yeah. It's going to work inside the...
And now the key question that follows is like, because this is Julia, have you tried to do whether this is actually differentiable? Everything like, can I propagate a dual number in this linear system of equations and get, the derivative of this?
Yes, in theory, it should be possible, right? Because we are not hard coding the vector type anywhere. So
right. So that's a very nice feature, I think.
Yeah. Yeah, it should be possible. Yeah. Yeah. And I think this is also very useful if you're interested in the algorithmic properties of the method, not only on the performance, right? So you want to develop a new preconditioner and you want to check how robust it is when you add more subdomains, for instance, right? And how robust it is when you increase the problem size. And you can do this in a sequential process to do these experiments. For instance, in this function, here I compute the number of iterations that it took the multi-grid to converge. And this P, with this P, we can tweak the number of parts, right? So this is like the sequential method in one part, but now let's see what happens when we add more parts, when we do data partition. Yeah, so the number of iterations has increased a bit as expected, right? And you can check how robust it is when you go even further, right? So now 27 parts, so it's robust, right? When we add more parts. So so if you're a mathematician interested in the algorithmic properties, you can use this as well. And at the end of the day, you will have a code that can be also deployed with MPI on a supercomputer. So you will have like the best of both worlds. So yeah, to do prototyping of your mathematical algorithms, but also to have a performant code to run on a supercomputer. Yeah,
That's
and I
very
think
cool,
with
yeah.
this I can finish the demo because we are starting to run out of time. Yeah,
It's okay. It's okay. Thanks.